Welcome to Physics Office Hours. My name is Eric. In this video, we are doing Introduction to Quantum Field Theory. We will be introducing Fock space with creation and annihilation operators, and we will be going all the way until we get the Dirac Field propagator. If you like physics, if you have any questions, I stream over at twitch.tv/PhysicsOH. Feel free to stop by and ask me any questions there. I stream every Sunday, Wednesday, and Friday. The schedule is in the description below. If you can't make the stream, feel free to hop in Discord and ask there, and myself or one of the brilliant community members will be happy to help you. I've also been toying around with a video from last week's stream on Green's functions, where we used the Green's function to get a scalar boson propagator. If you would like to see that, feel free to let me know either in the comments section or on any of my socials. And I hope to see you on Twitch. But let's see, let's get started with it. I like the following quote that shows up in the Lancaster and Blundell book at the very beginning. And maybe this might give a little bit more insight to the tuning fork, maybe not, I don't know. But it's every particle and every wave in the universe is simply an excitation of a quantum field that is defined over all space and time. So just like Dr. Lincoln said, you have quantum fields everywhere is quantum fields. But that doesn't mean much. What really means something, like where do we get particles and stuff from, comes from just exciting those. So how do we do that? Well, let's start by casting the language of quantum mechanics as a field. Now, you don't need to know all of the language of quantum mechanics to cast it as a field. We'll do something a little bit simpler than that. What we'll do is we'll talk about particles as creation and annihilation operators. So you don't really need, well, let me just explain sort of what we do with that. Let's start with ground states. Okay, so we'll have a ground state of many particles, which looks like this. There's a bunch of zeros, dot, dot, dot. I gotta move this bag. It's driving me nuts. I cord a little bit too. Okay. So let's start with the the ground states of a bunch of particles. So you don't need to know really much of what this is other than this is a bunch of zeros. Okay? And what these zeros are means that there is no particles. Okay? There are no particles in any single particle space. Right? This is what we call the vacuum. There are no particles. This is truly empty space. This is not physical empty space, but this is truly empty space. This is no particles anywhere. Now, this space, where we talk about zeros as opposed to ones or twos, where we might write something that looks like this, where we have 0, 0, dot, 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 and then we'll just have, one particle here, where the ith particle is equal to 1, okay? And what this is another state. We'll just give it a state, ki, where k is the momentum of a particle. This is called Fock space, where you have zeros for no particle, and then you have a number for where there is a particle. Again, if any of this doesn't make sense, please start asking questions. This is what we call Fock space. That's an O, people. Fock space. It was developed by a man named Vladimir Fock. In 1932. So let's see here. Now we can just have zeros for no particles, or we can just state the amount of particles that are in a certain state, wherever they are, whatever particle it is, and then we can just redefine this as a k-state where we have some particle in some state, and that's it. Particle, some momentum. And then we can write many of them, right? We could write a lot of them that look like this, and 1, and 2, dot, 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 and I, dot, 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 and which is basically, yeah, so we can write that. And that just means that there's particles in every state. Doesn't matter how many particles are in each state. We can talk about them as all being bosons or fermions or whatever. It doesn't matter. Well, fermions, you can only have a certain amount based off the Pauli exclusion principle, and yada yada. But nevertheless, we won't worry about too much about that. Now, what does it mean when we talk about a creation operator? Let's see. if we put a creation operator, so just imagine that this is a creation operator, and I'll explain that what that does, is it's basically adding a particle to a state. So this might be proportional, and the reason I say proportional is because there might be some eigenvalue associated with that, which we'll talk about that in a minute. But nevertheless, proportional just means it's equal to a constant times something, right? And what that something is literally all of the same particles in their associated states, dot, 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 with ni plus 1 now, because what we did was this creation operator created a particle in the ith state. And that's what I mean by this nice place of Fock space. We just have the amount of particles in each state, and we can use creation operators to add particles to each individual state as it becomes necessary. So then what we have, well, we have these creation operators, which I'll rewrite here, which is equal to, if you act on the ground state where there's no particles, and you add the ith particle, create the ith particle, then we get back to our ki state. That's the same thing as saying from here to here, right? All of these are zeros, then we add a particle. Adding a particle to the ground state gives you the k state. Annihilating a particle from the k state, annihilating ith particle from the k state, will get you back to the ground state. The create a particle gets you a particle, annihilate a particle makes that particle go bye-bye. These are what we call creation and annihilation. This is going from the first quantized state to the second quantized state. This is what Dr.
Do you mean the ground state as just the field?
No, the ground state's not a field. So in Fock space, it just means there's no particle here. So it's not a field yet. We'll introduce fields a little bit later. So the ground state is what you would consider like no particles. And then we'll have specific ground states mean specific things for certain things. But for this right now, we're talking about something very simple. 0 for no particles, 1 for 1 particle, 2 for 2 particles, so on and so forth. Is that making sense? How exactly does this thing describe where the particle is? We're not really worried about where the particle is quite yet. That will come later. Do you mean wait, wouldn't that be n plus 1i? No, the I is an index, so it's a label.
Do those symbols mean greater than?
So we have a 1, a 2, 3, 4, 5, all the way up to I. And this is just how many states. So the symbol is actually what's called a bra and a ket. This is a bra, where you have some state, and this is a ket. Now what this means is basically the state of a particle, right? So if a particle is in a certain configuration, like let's say spin up, then this state would represent the spin up. And we don't really need to worry about the complex conjugates. We might talk a little bit about that later. But as far, this is the complex conjugate of this. These are what you have in your badges if you're a sub. They're states. They look like this. But they're not greater or less than they're like quantum states. No, it is the Dirac notation. Oh yeah, there you go. Okay. Why would they choose such a confusing brackets? It's not as confusing if you do a lot of quantum mechanics. It's a language. So like once you learn the language of how to represent particles as states, it makes a lot of sense. But learning that language takes some time. I am not necessarily assuming you know the language. You just have to assume that this describes the particle in a certain state. And that's it. We call them states. Okay? So this is the in Fock space, this means that there's 0 particle. Then you create a particle in the ith ground state and you get a ki. And like this is kind of separate. Now we're going to make this much simpler by just talking about 0 states. So we're not going to worry about any of these extra things. We're only going to be talking about this one particle in the middle of the whole thing. Okay? So again, like just focus on there's no particles here. Then you create one, and then you have a particle with some momentum. That's the state. We're not worried about where in space it is yet. We'll talk about that later. And then here you go and you act with this particle with this momentum in this Fock space, and you get back to the ground state. Okay, which basically means no particles. Okay, so that's good. No. I'm glad you guys are asking questions. Please keep asking the questions. let's leave that up for a little bit longer. How do you account for the loss of energy then? So the energy we will add after. It turns out that, like, and I don't mean add after as in like we're adding it after. Once you get to the fields, then you'll start talking about the energy. For this, we're just talking about this magical land of Fock space. We're not worried about energy. We're not really worried about momentum. We're not worried about any of that stuff. That stuff will take care of itself later. But for now, we're just talking about whether or not there is a particle or there's not a particle, and how to put a particle where there's not. And then we'll take care of the energy later. It all takes care of itself in the end. Okay, great questions. Really, really good questions. Okay, next up. So from this, now again, we're just talking about this little Fock space. We can see some other relationships. Let's see what some of them are. We can annihilate on the ground state. And what do you think is going to happen if you annihilate on the ground state? Well, if you annihilate on the ground state, you're going to get a big old 0. No more state. Everything is gone. You get a 0. Okay? You cannot annihilate where there's no particle. That doesn't make any sense. So you get 0. Now, Tyrion, yep, you get nothing. Now, what happens if you annihilate on, oh wait, where did I go? Why did I do that again? Oh, I'm sorry, I misread it. What happens if you annihilate on on a different particle? How about we have the I annihilator, so we're annihilating the I state, but instead, what if we have a different state? Same thing, 0. We assume that if we're talking about a kj particle, then the ki particle is equal to 0. This is specific to AI being annihilated on AI, but AI cannot annihilate, or it cannot annihilate kj. That's 0. Guys, it's just harmonic oscillator. Is there a difference between the ground state and 0? Yes, the ground state is like the field, so the field is still there, and the 0 it's 0. And what that means, it doesn't mean anything really physically. Remember, this is just mathematics. So I wouldn't get caught up on a lot of physics behind this stuff yet. Maybe there is some deeper meaning physically. Justin or RPG or someone, what does it mean to annihilate the ground state? What is that? Is that anything? I think that doesn't mean like, or physicsy. Ooh, physicsy. Yes, the ground state is whatever state has the least amount of energy in general. That amount might be greater than 0 energy. Sure. Yeah, absolutely. Again, again, this is just like a 0. Yeah. Well said, physicsy. I'm not even going to try to adjust it. Notation-wise, you have an operator acting on a state to give you a scalar. Yes. Is that like the empty set and no set? I think so, right? Mr. Cultus, you cannot annihilate the ground state. Okay, so this is mathematics. We're not talking about the physics of the situation yet. This is set up in a very specific way. So I understand, Mr. Cultus, I understand why it'd be a little, you can redefine energy so the vacuum has 0 energy. Sure, you can, I guess it's like gauging, right? Gauging? So the idea behind annihilating the ground state is to get it out of the equation. You don't actually do anything physically there. So remember, Fock space is like, I know that there's a lot of physics behind it, but there's not like having 1 or 2 particles doesn't really tell you anything about the energy or about the physical state of each particle. It just says whether or not there's a particle there or not a particle there. And you can, like physics, he said, you can have energy where there's not a particle. That's the vacuum energy. We've talked about the vacuum energy a bunch. You can annihilate the ground state, but that just provides you with a new state that has 0 amplitude. Right. So it will show up that like that will go away from the equation and we don't actually consider it. My biochem brain is picturing charged particles and excitations dropping back down to the preferred state. Yeah, so this is pretty different than chemistry and the chemistry applications in physics. That's very quantum mechanical, and this is another step farther. So this will make sense later, I promise you that. Never happened. And then there's one more that we have to talk about, which is, lost it in my notes, there it is. What if we annihilate, and this works for creation as well, what if we annihilate the state, or can we rewrite this in a different way? And we can by saying the delta function. Now, if you don't know what the delta function is, it's the combination of this right here, I, and double I. It basically means Dirac Delta is equal to 1, or I'll start with 0 when I is not equal to j, and 1 when I is equal to j. So remember, i's and j's are indexes. We can let them be whatever they are. They can be 1, 2, 3, 4, 5, 6, 7. We can let them be equal if I is 1 and j is 1. So if I is 1 and j is 1, then here we get I is equal to 1, I is equal to j, which is equal to 1, and that just means that this out front is a 1 with the Dirac Delta. So what does that mean for this one? Well, if I and j are not equal, so if I is equal to 1 and j is equal to 2, there is a 0 in the 2 spot, so you can't annihilate, or you know what I mean. So if I is 1 and j is 2, then there's a 0 in the 1 spot, and there's a kj in the 2 spot, so you can't annihilate 0, so it goes to 0. So the Dirac Delta makes this one a little easier to handle. If you annihilate the ground state, you get literally 0, not 0 state, right? This is analogous to representation theory in the highest weight state. Looks like set theory. It does look like set theory. Not Dirac Delta. Right, Chronica Delta. Thank you, Admiral Entropy. Love your name, too. States are states. The ground state is the lowest. You cannot annihilate. You just get 0 if you try. Exactly, Mr. Cultist. Exactly. That's what I'm saying. If you annihilate the ground state, you get 0. Perfect. And that what Justin is saying is that you get, and this 0 is your contribution to the probability that you'll get that state. So you get a 0 probability of getting that state. That's why it's not physical. Because you always get a 0 probability. I think we're all in agreement. There is some issues with the understanding the different languages that we're using. But we are all in agreement. Okay, so let's move on. Again, the VOD of this will be available. This will probably get turned into a YouTube video, so stick with me on that one. It's intro to quantum field theory. We're starting at second quantization and getting to a propagator. I'm not familiar with deltas. I will just hope that I can continue to follow along. Yeah, the deltas are literally just like, it's just shorthand. It's literally 0 or 1. Is it chronic? It must be. Yeah,
what happens when you use the creation on a state that already has a particle?
You add more particles to that state. So there's issues with the statistics if you try to, the statistics will take care of if you're trying to add particles to the same state, you'll get zeros and everything like that. But again, I don't think we're gonna get that deep into it. That one, you'll have to wait and read your book. Is it infinite? I mean, not physically, obviously. But mathematically, you could probably add infinite bosons to the same state. And then you can use bosonic statistics to handle it. I imagine it turns into garbage. Because that's not physical. Where are we at? Okay, so from this we need to understand commutation relations. This is the interesting part for this little tidbit. So we have the commutator, which we've seen many times, right? Commutators, which is A, B is equal to AB plus, nope, minus, sorry. And AB plus BA. And if something commutes, so if commutes, then A, B is equal to 0. Okay? And then anti-commutator, that's not. Your Fox space is probably infinitarian, but not necessarily so. Well put. Yeah, I can imagine you can add whatever you want in Fock space. It's just like I said, I think the physical, there's physical limitations to stuff. So the anti-commutator is just changing the middle, and the same thing. If it anti-commutes, then this is equal to 0, okay? So we'll just do 0 if anti-commutes. Now, think about this with this commutator. This is a little bit interesting because not everything in particle physics, or quantum mechanics for that matter, commutes or anti-commutes, right? Like, think about this. What if you had two numbers? 2 times 3. Well, you get 6 minus 6. That's going to equal 0, right? 2 times 3 is 6. 3 times 2 is 6. That equals 0. So in numbers land, where we normally do basic, our basic algebra and things like that, we know everything commutes. It's commutativity. That's a property that we study when we start learning math. But now, in physics, we have something where these don't do that, right? We have operators that don't always commute. Let's talk about them. We can make a little table even for separate statistics, where you have bosons, which is like your photons, your gravitons, all your different other particles. Order matters, BA or AB, exactly. Commutes means order doesn't matter. Well put, Will, definitely. Matrices are simple mathematics examples for if they don't commute, yeah. Yep. And there's a lot of matrices that do commute. Like these are all operators. They can be cast as matrices, and we can find that a bunch of them do commute, right? Like AI dagger and AJ dagger. So two creation operators on separate particles or equal particles. It doesn't matter if I equals J. It doesn't matter if they're both creations, they're always going to commute. Right? Now these are bosons. Same thing if you try to annihilate particles. Where did the music go? It's like a set without anything in it, or an empty set. So in Fock space, you could think of it as like a set without anything in it, like an empty set. But the energy is different. It's like there could have energy. On the ground state, this does not give you the ground state. Right. Okay, good. I still think we're all on the same page with that. Now, bosons also have the last commutation relationship, that it is where they actually do not commute, and you have AI as an annihilation, AJ as a creation operator, and these actually equal that Dirac Delta. Where if this I and this J are the same, then there is a 1 here, but if this I and this J are different, then there is a 0 here, and they commute as well. That's bosons. We can do fermions. Fermions are written the same way, except now, literally they're identical, except one difference. Instead of commutators, we're talking about anti-commutators. Again, all of these operators are the things that we work on in Fock space, but very soon, we will not be in Fock space. And again, anti-commutation, so they have the plus, but it's still that Dirac Delta. Okay? Keep this one in mind. This one's special. We'll talk about it in a second, too. Now, there's a big issue here that a lot of people have already asked and talked about, right? The issue, namely, is fermions are weird. Yeah. Fermions are weird. You should try paraparticles sometime. Even weirder. Just with a whole bunch of harmonic oscillator. Yeah, so there might be some issues with this picture, right? One of the biggest issues is we don't actually have a way to talk about energy. How about spin? How about all of these different things we need? But I am done with Sakurai. All of this is from Sakurai. If you have the Sakurai book, this is following pretty much straight from Sakurai. And this is all the second quantization stuff. So now we're out of you guys, if you did quantum mechanics, you're gonna see a lot of operators like X hat and P hat and all of this jazz, blah, blah, blah. In second quantization, you go right to Fock space. You go with the A's and we'll also see B's. And then some people use C's and D's and it gets a little messy. But let's introduce something else. Let's introduce a field. Now this is the moment you all been waiting for. I will be putting up the spinner video next. And it's, again, just sort of describing what a spinner is. I will give you a little bit of math to go with the spinner, but not a ton today. And I'm also not going to describe a spinner too much. I'm just going to say the following about the spinner.
Why commutator vs anti-commutators? Because of the exclusion principle.
Yes, exactly. You still have your copy somewhere, Admiral. There you go. Sakurai's great. Grassman path integral is so weird. I do those all the time. Okay, so let's do the field. Now, I'm going to pick kind of a complicated field, but you could do scalar bosons. It's a lot easier. I want to do a Dirac field. So, like the Dirac equation, right? So something that solves the Dirac equation, because I know some of you have your hand in the Dirac equation. I don't know why I chose it, but I did. And that's what we're doing. Now, the field that satisfies a free field Dirac equation is led by symmetries. A lot of you may not know what that means. Don't worry about it. Don't worry about what all that stuff means. But if you do know what it means, that's what we're doing. Now, basically, this is the field. This is the field that Dr. Lincoln was talking about. This is how we describe it mathematically. This contains all of the energies and the things that Sarah was slightly concerned about, which rightfully so. And this is what we need to know to talk about the particles in their entirety. Spin is going to equal 1 to 2 because it's a Dirac, and you have, 1/2 or, it's just, there's two spins. There's up and down. That's why. So we have a U, which is the spinner. Now the spinner is going to control what the particle looks like spinning, chirality and helicity. I have a YouTube video about that if you're interested to know what the differences between chirality and helicity. These are Dirac fields, so they're going to experience chirality, and that just describes what the particle is. Now this is the entire field in all its glory. We won't need nearly this much to talk about it, but I'm going to write the entire field down in all its glory so you can see it. We have the A's and B's are now going to be our creation and annihilation operator. The A is for the particle, creation and annihilation. The B is for, if you can believe it, it is for the antiparticle. So we want different ways of describing particle and antiparticle. In hindsight, if I did the scalar field theory, which is how you normally learn the subject, it might have been a little easier to understand because there's all A's because they're their own antiparticles and we don't have to worry about it too much. But I did not. I wanted to see something that you guys might be more accessible to. So we're going to do Dirac fields where you could do like a free propagating electron or something along those lines. Hydrate. Thank you so much. I am super parched. Thank you very much, Noel, for the hydration reminder. I met the last Blackboard full on the stream. Boson Fermi. Yeah, that's. I get it. I definitely do, Dusty. This was certainly. So this was a request by a lot of my viewers to go over this. So I'm glad we are. So this is the field equation. This tells you everything about the particle. It tells you how to create or annihilate particles and antiparticles inside of the field, right? So, where A's, and we can talk about A dagger and B dagger, are the creation operators for particle, antiparticle, and then A and B are the annihilation. All right. Now, we can show you what it looks like with this whole thing, and it's basically like pretend we want to talk about electrons or positrons. Well, how do we create an electron?
What is U and V? What is the factor dividing the integral?
Okay, so the factor dividing the integral is where the energy. In order to get it, it's a little bit more complicated. You'll have to wait till your book gets in. I'm not going to show it. This kind of shows like the energy, and this takes care of the Dirac Delta function, which I'll introduce later. Again, this is the energy, and then the U's and the V's are spinners. We'll talk about them in a second. But for now, let's talk about these. These are the same things we talked about before. They are how you create and annihilate particles in Fock space. So let's say, what if we want to create a electron? We'll talk about creating, so we'll take our creation operator. We'll act on the ground state. And then what's the state going to be? Well, it's going to be some state with an electron and the given momentum and the spin of that electron. Same thing with the positron. You can do the same thing. Act on the ground state, and you'll get some positron state. Now this is just the state. It doesn't mean much, but this is the Fock space, right? So here you have the ground state. Here you have an electron. It doesn't really tell you anything about the electron. It just tells you that the electron is there. In order to get to know about the electron, we need to talk about the spinors. So we have U. The whole combination of these things kind of tells you what, so this is the particle, this is the antiparticle, and these are the spinors. This tells you how the particle looks and how it's moving. Spin, and like the chirality will tell you the direction it's propagating, the spin of it, and blah blah blah. Okay? Which will matter for like energy conservation and momentum conservation. Is that the beginning third order derivative with respect to the occupation number or what? No, that's actually real space, momentum 3 in 3 dimensions. Yeah, physics got it right. Like it's a volume term. It is a volume term because this is, did he answer that one too? Momentum, no he didn't. Oh, volume, yeah, exactly. There it is, beautiful. Okay, wonderful. Thank you, PhysicsOH, for the help. Great questions. Mr. Cultus and others. Dusty, keep going. And Admiral, you're doing good. This book, is Langacker. Paul Langacker's The Standard Model and Beyond. Alright, so these dictate, like I said, these dictate your chirality, your momentum, your direction, and blah, blah, blah. So let's talk about the definition of a Dirac Delta. Now, that Dirac Delta, so the Kronecker Delta is one thing, the Dirac Delta is a different thing. We won't go into too much detail about the Kronecker, or about the Dirac Delta, but I'm going to show you the integral form, and what the Dirac Delta basically, it's kind of similar to the, Dirac, or the Kronecker Delta, but there is some differences, and we won't go into them too much. I will just show you what the Dirac Delta looks like in terms of Feynman diagrams, but before we do that, let's define the integral of it, the integral form of it. For those of you who don't know, we'll have the integral of -I 2 pi, and when we get 3 of these, we're going to need to cancel out that, which is why it comes into play here. But this is the Dirac Delta function in integral form, and these are size. I don't know why they have size, but this is straight from the wiki. And if you have two variables, psi2 minus psi1, the integral of, so it's going to be -I 2 pi psi1 minus psi2 times t dt, and this is an e, then this is going to be equal to the Dirac delta of just psi1, or psi2 minus psi1. Like I said, if you want to know more about this, Dirac delta functions usually just show you where a function spikes to infinity, and you can go ahead and look at, the integral of that is 1 usually, but you can look at this stuff up if you want to. This is usually introduced to you in your 3rd year of physics in electricity and magnetism. At least that's where I saw it. So it's not super inaccessible if you want to understand it. But we'll talk about it in a different sense a little bit later. So this is the Dirac delta integral form. Pay close attention to this thing because it's going to show its ugly head again soon. And now what do we want? So we have a field. We have, in the field, we see our spinors, we see our creation and annihilation operators, different order. And then we see that the one's creation for a particle, one's creation for an antiparticle, and blah, blah, blah. So let's do something with it, right? We have introduced everything to set up a field. Now we want to actually apply this. How do I learn integrals? Most of the time I see really fun theories about, calculus 1 and 2 is really how you learn them. Can we use this to know where the electron is relative to some local point? You can. Most of the time you don't care too much about where it is, you only care about how it looks. And I'll explain that in a little bit more of a different sense. We really want to know in quantum field theory how things behave, right? when in light of something else. So when you talk about charge of a particle, does it really mean to talk about charge of a particle as just like the charge of itself? Or does it make more sense to talk about the charge of a particle as its influence on something else, right? And this charge, and we do this, is really the coupling constant. I won't get into that today, but you can look that up. And it's really the influence of one thing on another thing is going to be the coupling constant way of looking at things. And that coupling constant will then extrapolate to the charge of a particle. So it doesn't make a lot of sense to be like, where is something? What's its charge? You know, how is it spinning? It's more about like, how does this particle affect this particle? If I have, like, with how much probability can I get these particles to scatter off each other? Let's see, you can think of the Dirac Delta as just a Gaussian curve where the width keeps going down, but the height keeps going up in such a way that the Gaussian stays at 1. Awesome. Well, very, very well understood. Okay. Look at that. Physics coming through with great explanations. Thank you, PhysicsOH and Justin and everybody else who's helping understand this stuff. Let's see what to do with this. I will erase. I don't want to erase this. I don't want to. I want this to stay here. Xi 2 minus Xi 1. I know I'm saying Xi. Some people say C. Whichever terminology you are interested in the most, keep. All right, so we're going to condense these down to something a little bit more stomachable, a little more palatable even. And more interestingly, we want to know about the following. What happens if I take the anti-commutator of a field, we'll say at x1, so here's that position, and a field at x2, so different position. And we'll take the anti-commutator of that field. Why? Well, eventually you want to know how things work in a vacuum. So you could stick this in a vacuum, and you'll get this very thing. This is the goal. We want to understand how things behave in a vacuum, and especially for a free field. If it's a free field, it means it's not interacting, and it should propagate directly through that field, right? Okay, so how do we do this? Well, we know what the fields are, so let's take a little look at these a little more openly. And what we'll get is the following. We'll get some integral with some sum over spinors, blah, blah, blah. We're not going to worry too much about that stuff. All of that stuff out front. What we really care about is our newfound knowledge of how these things behave in Fock space. So let's recast these and right here we'll say this is where the spinors live. We'll talk about them in a second. And then we'll have e to the I xi p minus xj p. Let's not say p, let's say q. Let's associate the particle, this particle, with a q, a different momentum. Only to convolute things for you guys, because I love you. And then we're going to add to it the rest of it, which is the antiparticles terms. I will make one statement, and this is probably going to be one of the most confusing things I said all day. You may be wondering where the A dagger and the B not dagger come from. Minus I xi p minus xj q. And the A dagger and the B not dagger come from this guy. I showed you what this is. If you dagger it, it's basically like switching the A's and the B's daggers. So like if in this one, we saw A and B dagger. In this one, you'll see A dagger and B. That's the best way to think about it. It's called the Hermitian conjugate. But the terms are somewhat meaningless to me right now. Oh, I see. I know it's a little bit more complicated. Yeah, but it's taken to the absolute extreme. Oh, yeah, there it is. Great. Okay. If you want to see how the spinors behave, there's going to be spinors here, there's going to be spinors here. The spinors behave the following way. If you sum over all the spins, you'll have U and U bar, which is, you get U bar from the conjugate, or the Hermitian conjugate. And that's going to give you the following, which is P/plus M. This is not the simplest to understand. it's basically like the momentum plus the mass. If anybody has another way of thinking about it, the slash means you add something called gamma functions to take care of the dimensions and other things. We won't talk too much about them. But just think of it as the momentum plus the mass and the momentum minus the mass. This is all RPG. This is you. Relativistic kinematic stuff, right? This is one of the very first things you learn when you enter the field is how to where this comes from and how to handle it. Gath! Hi! Good to see ya! Can I get a shout out for Gath, please? Thank you so much. Okay, now. So we have our new form where this is equal to this. And like I said, we have, you know, the one part, this one's going to annihilate the particles and create the antiparticles, and this one is going to create the particles and annihilate the antiparticles. That's just sort of, it's all complete now, right? We have both options on the table. We can either create and annihilate or annihilate and create, and now that we have an anti-commutators around it, we're gonna see every option for this, right? We're gonna see every option of creating and annihilating a particle, antiparticle, or antiparticle and particle, right? And, okay, so let's get a couple things out of the way. We know, because this is a free field, that P is equal to Q, which is also equal to negative P, right? If the particle of 1, if the particle going in is the same, momentum of the particle going in is the same as momentum of the particle going out, we can recast it in the following way. And remember, anti-particles move with opposite momentum, so yes, we'll have to worry about that too. But we're almost done. We literally have 2 lines of notes left. If you enter this into here, you'll change the signs of this, right? And how will you get this? You will end up looking like something like this. The anti-commutator of sine xi, now it's just like some random xi, and some psi of xj, but this is dagger, is going to equal the integral. Remember, all of these are taken care of. We're gonna throw them away for now. You can bring them back in at any time. This is just momentum and mass. I'm only worried about what's going on with the particles, not the way they look and how they interact. I'll show you them later when we get to the Feynman diagrams, but I won't talk much about them right now. Instead, let's talk about the final thing, which is d3p over 2 pi 3, to the third, I mean, times e to the plus I p x I minus xj. Now, this p, again, comes from, and this is a vector too. I mean, I haven't been writing it. We kind of been dropping the vector signs, but you get the picture. And this again comes because the p, I set this q equal to p, and then I changed the overall sign of the p and got it to be all this thing. I want it all to be the same p. So okay, so physics is on it. Wonderful, thank you. Okay, so what does this equal? Well, this is our friend, the Dirac Delta function. Notice the t is the p, integrating over dt, except there's 3 of them. And then we have a 2 pi up here, and a 2 pi down here, so that will cancel away. So this really is equal to a different type, like the last one we had the Kronecker delta, but this one we have a Dirac delta. And what does this mean? This means that if I and j happen at the same place, if it's the same place, then what you can get is, oh, well, I should probably write it the correct way, right? Which I have in my notes. There's a 3 here because it's 3-dimensional, xi, xj. And if you had the ground state, the only difference would be, since this is a factor of constant, it's either 1 or 0. And then, yeah, it's either 1 or 0 because there's some other stuff involved. Then this, you know, you would pull it out, and then you get the 0 state times the 0 state, which is just 1, because it's the same state. And the inner product of a state with itself is 1. And we've done it. This is what we talk about as a Feynman propagator. If you apply this to the vacuum state, we'll just simplify by saying psi I and psi j. Psi dagger j, excuse me. Then what you get is this times this, which is 1. And of course, you're going to get this prefactors, which we'll show later too. But this is it. What's the Feynman diagram? This one's an easy one. This is a propagator. Oh, this P is momentum, not for propagator. But that's it. The particle can go. This can describe a particle going into, just a particle going into an antiparticle, or an antiparticle going into a particle, or a particle going into a particle, or particle going to particle. It can describe all of this stuff, and it all happens from the field. Now, this isn't an interaction. This is just a free field. So really, I think you're kind of stuck with a particle creating and annihilating itself, or an antiparticle creating and annihilating itself. But those are pretty much your options. But that's where we're at. We've done it. We have gone from talking about how these things create something in a zero state to talking about how we can actually have a particle propagate through space. It's like teleportation. It is, but it's also kind of just like, we think about a particle like, we don't really think about a particle propagate, like, you can think about it a couple of different ways. You can think about a particle like teleporting, or you can also think about a particle just being like here, 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 and every time you go to a new space, you're actually annihilating and creating in that space, and then annihilating and creating in that space, and annihilating and creating in that space. It's really just like the same, like everything is the same all the way through. And turtles the way down. Whew. So let's take a look at a couple more, we is done with the complicated part. Now the fun part is looking at what this looks like in a larger sense, right? So here we see the field commutations. You see the whole thing with the 2 pi to the third and the different deltas, the Dirac Delta and the Kronecker Delta, and then the Dirac Delta, and the R and the S are the spinors, so there's a delta function associated with the spinors and everything as well. If you're into that type of math and you want to get to like the deeper, more calculation stuff. So here he uses a B and a C, but the process is the same. He has this is supposed to be an anti-commutator. I don't know why some people are just, they don't care and they'll just always use square. Some people mix up the squares. I don't know what the whole deal is. Oh, I didn't mention that the B's have a different sign out in front, but the B's actually have, when you're talking about the B's and the delta functions, B's always use a negative, like antiparticles for fermions always use a negative. They're equal to the negative delta, and they're not equal to the positive delta. I forgot to write that down. I'll have to add that in afterwards in the edit. But that's the way to get this to work out so that you can see how this is the Dirac delta function of x and y, or xi and xj as I used. So we can scroll down a little bit and we'll actually take a look at some of these different Feynman rules. This is how you derive the Feynman rules in various ways. There's shortcuts, like once you do this enough, you start to recognize a pattern. That pattern turns out to be Wick's theorem. Wick's theorem makes this a lot easier to kind of get around. And it makes it a lot faster. But this is the propagators like we talked about. And what does it actually look like in a graph? Well, we can show you the different equations. They go through all of them. So these are kind of like your basic Feynman rules for fermions. You have an option, a leg. This is not a propagator, this is a leg. So the particle comes into an interaction. So in the middle you have a vertex and an interaction. And then you come out. Now each internal line so these are basically rules. So to each incoming fermion and momentum, if you're interested, you can look at all this. It tells you all of the different rules associated with the Feynman diagrams. You can see this is the incoming fermion with momentum p, and this could be like an associated outgoing one, so it'd be like the opposite, you know? And then there's the anti-fermion, antiparticles, right? Going in and out. And then there's the rest of the rules. Like what does a vertex get, right? Looks like trees. These are called tree diagrams, actually. I don't know if that was a joke or not, but these are actually called tree diagrams. From discrete math, I think it's the same idea. There's no loops in it. We do loop calculations, but they're far more complicated. And that's when you have to start entering with extra internal lines. So for higher ordered Lagrangians, which we didn't even talk about Lagrangians. I didn't want to get into it, but that's where all of these, that's where you're going to get the actual interactions that are going to lead to the diagrams. Is you find a Lagrangian, like the quantum electrodynamics, QED has a Lagrangian associated with it, right? The Lagrangian derived from all the symmetries that we see in nature regarding electrons, positrons, photons, muons. You get the point. Electromagnetic stuff, right? From those Lagrangians, you can actually find the interactions, and those interactions are what we use to make these tree diagrams. And then higher ordered Lagrangians, like maybe you have L squared, L cubed, then you'll start to see loops inside of these diagrams when you start to get many multipliers. I don't think they're very related, like binary trees and such. Okay, I don't know anything about that. But maybe I thought that maybe they were just the similar name. But if I don't know what binary trees are in computer science, but I think it might, yeah, I guess it's probably, if physics says it's different, I think it's weird. But then we can see these, and we didn't see what these were in our initial state, but look at, for fermions, we have these p plus m and p squared minus m plus IE. This is that EP squared that we saw, the energy in the bottom. Let's see if we can find it really quick. Never mind, I didn't write it again. But this is that E sub p that I wrote in the original equation. And then this is that p slash plus m you get from the spinners, right? Taking care of that momentum plus mass. And this is really going to be the propagator. This is going to be the thing that's in the middle. So one diagram you might see this in, I'll do it in this little box here, would look like this, right? You know, you got particles coming in, and then let's do a realistic one. So in quantum electrodynamics, you might see something like this. A photon comes in with like an E. Who cares? Plus or minus doesn't matter. Then the E minus plus doesn't matter. And then photon comes out, so gamma, and then this would be the E plus E minus, right? So we'll just stick with one. So we'll say positron, and then positron comes in, an antiparticle comes in, annihilates with a photon. You get the propagator, and then each position here is a vertex, and then you get the external legs going out, a photon and a electron. You can do the same thing with scalars. Why did you jump in with fermions instead of doing the easier boson? I don't know 100%. So I wanted it to be something a little more tangible. The scalar boson, like what he's saying, the easier boson in the Klein-Gordon equation, that's a lot easier.